Hello and welcome to a video on feedback basics. In this video, we will first have a look at the difference between positive and negative feedback, then at sampling and mixing, since feedback is the measurement of output and manipulation of a system. Then we will look at some properties of negative feedback. So what do you stand to gain out of adding feedback to amplifier? And then just some basics around the four different amplifier types and the feedback topologies that's used for um, each one of them, stemming from sampling and mixing. So first up, positive feedback. Positive feedback is generally, when we're dealing with amplifiers and trying to stabilize an amplifier, a big no-no. Positive feedback is known as regenerative feedback, and in short, if we insert a small signal into our amplifier, we get out a large signal, and that a portion is taken of that to the back here and then added to the original input. So this means that your output will grow and grow and grow and become very, very unstable. Okay, so positive feedback typically gives us unstable systems. So that's why it's used for oscillators and astable systems. And the feedback network is typically some RLC kind of network, and there is in general no input on a system like that. So this is more for oscillators and such. So we are more interested in negative feedback for this chapter. So it stands as degenerative feedback, and we use it to stabilize the gain of a system. And the feedback network, the beta, is typically a resistive network. So having a look at it is we have some input, some output, and if we have a output divided by the input, it will give us the gain of this system. Okay, A0 is some amplifier with a gain of sorts, and beta is some fraction. Okay, so the output of amplifier is sampled by the beta network, okay, or measured, and then it gives us a signal called XF here, or the feedback signal. So the feedback network can be defined as XF because it's its output over XO because it is its input. Okay, so there is our feedback network, and that is also some form of gain, typically the inverse of the amplifier's gain right here. Right, so right here we have X in and XF being subtracted from one another, and that provides input to our amplifier, which in turn gives us X out. So that is our second equation. X out is A0 times X in minus XF. So then we can plug this XF into that position right there, and we are left with X outs, X ins, and X out. And that can give us X out over X in, which would be the gain of the entire system, like that. So AF, or the feedback gain, is x out over x in, and that will give us a0 over 1 plus a0 times beta. Now this 1 plus a0 beta is our desensitivity factor. In some books or places you will find it as D, and that will be the amplifier's gain with feedback applied. So I used x's here because this can be currents, it can be voltages, doesn't matter, it will be the same for all four amplifier topologies. Now the good thing is, if our gain were to be infinite or extremely large versus the feedback gain that we want, then AF will boil down to being 1 over beta. Now this you have seen probably with operational amplifier circuits where the gain is purely dependent on the feedback network. We take an op amp, you give it some resistors, and the ratio of those resistors gives you the gain of an amplifier. So if the gain of amplifier is large enough, the feedback gain will tend to be 1 over beta. Okay, so there is cases where the op amp's gain is not high enough, and applying the resistors you will not get the gain that you are catering for with your resistive network. Right, so the main takeaways from this equation is AF is 1 over beta. So if you need to design a beta network or a resistive network initially to go with your amplifier, you assume that your gain is infinite, and you can design your resistors using this equation right here. But in the end, this equation, when you have your amplifier gain available, will provide your amplifier's actual feedback gain. Okay, so these two equations is very important, and this top one right here, when defining our beta network, is also quite important. So before we look at the properties of negative feedback, let's have a look at what sampling and mixing means. So sampling here is how do we measure the output of this amplifier, and mixing is how do we apply the feedback to the input. Right, so the top here is all on the output side, and the bottom here is all on the input side. So top is sample, bottom is mixing. So if you're dealing with a voltage output and you need to measure the voltage output, we always measure voltages in parallel if we have to use a multimeter. So put this image in your mind. If you need to measure a voltage, it should be in parallel or shunt. Okay, so from now on, we're going to use the word shunt. It is just a pretty word for parallel. Right. If you need to measure a current, you will do that in series using a multimeter. Okay, so voltage measurement is shunt, current measurement is series. The input side, or when you need to add the new fraction that you measured back to the input, voltages are added in series and currents are added in shunt. Right, so if it's a amplifier that takes a voltage input, you need to add a voltage to that voltage, so it will happen in series. If it's a current input, it should happen in parallel, in shunt. Okay, so let these four figures be the guide to when you are trying to figure out what feedback topology you are working with. So we will look at this more when we doing the extra videos after this on voltage amplifiers, current amplifiers, and so on, and the feedback networks with them, and how to analyze those feedback systems. Right, the properties of negative feedback. So the first and important one why you typically will use feedback is to desensitize the gain of amplifier. You want a specific gain, so you choose your feedback network to achieve a specific number. Okay, so desensitivity of gain means that the gain of amplifier will be less sensitive to variations in gain due to temperature changes or variations in components, which is a fair thing. Op amp is a bunch of transistors, and you can buy 20 of them, and not one of them will have exactly the same gain. But when you apply resistor feedbacks to them, they will all produce the same output, the same gain. Okay, so feedback is to make processes a little bit more precise. Right, so feedback is one of those things that can fix a lot of problems that you have with your analog electronics. Right. The next one is to reduce nonlinear distortions. We will have a look at a few pictures in a moment. So if there is different gains because you cascaded a bunch of amplifiers, all of them will have different slopes to them when being multiplied one after the other after the other. So your feedback will fix the nonlinear distortions that come of cascading multiple amplifiers. Thirdly, it will reduce noise. Okay, so noise due to temperature changes and those variations. Feedback will reduce noise in your system. Then it exercises some control on your input and output impedances. So depending on the amplifier type, if there will be increases or decreases in the input and output impedance, we will lastly have a look at those, what will happen with your different amplifier types. And lastly, it extends the bandwidth of amplifier. So what happens generally is the more you increase the gain of amplifier, the less the bandwidth becomes. So technically, when you're applying feedback, you push that gain downwards and you spread out the bandwidth a little bit. So as a figure, this black figure here at the top is the gain of our amplifier without feedback applied. Now the moment that feedback is applied, our gain is brought down, but our bandwidth becomes larger. Okay, it's not like it spreads into these areas, it's just measured at a different point right here. So By applying feedback, we extend our bandwidth. And you'll find with op amps, if you boost the gain very far, that you almost have no bandwidth at all, and the frequency ranges you can work with is extremely small. But when you apply feedback or reduce the gain, that bandwidth typically becomes larger. So it's the same principle right here. It's exactly the same thing. As example for reduction in nonlinear distortions, the class B amplifier suffers from this crossover distortion right here, and one of the fixes is to put the op amp here and feed back the output into the op amp as a buffer configuration, and this area right here is not removed, it is reduced. Okay, so this crossover distortion, this 0.5 volts, is divided by the gain of the operational amplifier and thus decreased. Okay, so that is one of the properties of negative feedback where you can clearly see it, and I've done this in my video on class B amplifiers. The second one is if you are cascading a bunch of amplifiers. So A here is two amplifiers that's added together, and this is the effect of one of the amplifiers has a very large gain. The second amplifier doesn't have such a large gain, but it has a better output here. And by applying the feedback, note that these two lines are almost 100% in line. So by applying the feedback, these lines have been stretched a bit so that they almost conform to one another. Okay, so if you have infinite amount of gain, these two will be straightened out almost completely. But yeah, so that is the reduction in nonlinear distortions. On to our four amplifier topologies. So the next four videos we will look at each one of these topologies, and the first one will be the voltage amplifier, also the series shunt feedback topology. Now this name right here has to do with amplifiers, sampling and mixing. So let's jump to the last 2 points right here. It's voltage sampling for a voltage amplifier, so that happens in shunt, and voltage mixing at the input, and that happens in series. So the name describes the mixing and the measuring like that. So it is a series shunt topology for voltage amplifiers. Right. The gain is in volt per volt. The feedback factor is in volt per volt. Now, ideally for voltage amplifiers, you want the input impedance to be infinite. So applying feedback will increase your input impedance. It's a good thing. And you want your output impedance to be typically zero. So the feedback will decrease your output impedance. Okay, and everything always happens in this 1 plus a beta kind of factors with feedback. So there is an increase, the entire input impedance of amplifier will be multiplied by 1 plus a 0 beta If there is a decrease, it will be divided by 1 plus A0 beta. Right. Current amplifiers. Current amplifiers needs to have a very small input impedance and it needs to have a very large output impedance. So we have a decrease at the in, we have an increase at the out. So there's not much to remember about these equations. If you can argue the amplifier type and what kind of input and output it should have, you should know what equation to use for input and output impedance with feedback applied. Okay, for the current amplifier, current sampling happens in series and the mixing happens in parallel or shunt. So current amplifier is the shunt series topology. Right, transconductance, series. Current being measured in series at the output, voltage being mixed in series at the input, and the transconductance amplifier takes in a voltage and gives out a current. So for voltage in we need a high input impedance, for current out we need a high output impedance. So both will be increased with feedback like that. So both is being multiplied by 1 plus A beta. Our last amplifier here with trans resistance amplifier. So the trans resistance takes in a current and provides a voltage. So it will have voltage sampling, which happens in shunt. It will have current mixing, which happens in shunt. So the trans resistance amplifier is shunt. Taking in a current, you have a low input impedance. Providing out a voltage, you have a low output impedance. So both would be decreased while applying feedback for our amplifiers. So that is the introduction to feedback. The next 4 videos will be on the 4 different topologies right here. So we will start with the voltage amplifier. Thank you for watching and see you in the next video.